Solutions to the Chapter 9, which is Momentum Homework Problems, screencast. So you can either look at this as a PDF or a screencast. Hopefully you love my voice. I don't, but hopefully you do. At any rate, I'm going to go through some of these. A couple problems here had ms as the time, that's milliseconds. So 1 millisecond is 1,000th of a second. So the idea, it was give you this graph, asking about the impulse. The impulse is the area of the graph, so I don't need calculus for that. I do just need to figure out the area of that rectangle and the area of this triangle, and that gives me 4 Newton seconds of impulse on the object. Problem 12, it gave you an initial velocity and a graph of force versus time, and asked for the final velocity. Told you the mass of the object was 250 grams. So at that point then, you can find the impulse. So the final momentum is equal to initial momentum plus j, which is the impulse, and that's F delta t. So I ended up getting a final momentum of plus 1.5 kilogram meters per second. And then if momentum is equal to mass times velocity, put the mass in, got a final velocity of plus 6 meters per second. So that was the rebound velocity. And that would be in the positive direction since this initial momentum was in the negative direction. For problem 15, it was a train car, and it was raining into the train car vertically from above. Initially, the train was going 22 meters per second, and at the end, it was going 20 meters per second. It was asking about the mass of the rain. So solve this using momentum initial equals momentum final. The speed lower, therefore the mass has to be higher. And I've got 500 extra kilograms of rain. That's 500 cubic meters. Considering that I don't think a train car is that many square meters, it might be like, I don't know, 5 times, maybe it is. Yeah, that would be a very heavy rain, I think. At any point, moving along here to number 26, this was the F max, and it basically showed you the force versus time graph. It says a ball has an initial speed of 32 meters per second, rebounds with the same speed, so that means it's going the opposite direction. So the first thing is I find the area of the graph. It's 1/2 F max times 0.02 seconds plus F max times 0.02 seconds plus 1/2 F max times another 0.02 seconds. So you could also think of the area of a trapezoid. So I get that the area is 0.004 F max. The second thing is to find that impulse. Well, the mass of the ball was 60 grams, so that's 0.06 kilograms. And if you're going to bounce back the opposite way at the same speed, that means you have a change of velocity of double the speed. So I have a 64 meter per second change in velocity. So that means my impulse, or change in momentum, is 3.84 units. So then I can solve for the F max as 960 newtons. P32 is using calculus. So again, you're going to use the power rule. If you had the momentum is 6t squared kilogram meters per second, then the force is the derivative of that. That's 12t kilogram meters per second squared, and that is a newton. Why? Because m times a, kilogram times meter per second squared, gives us a newton. This one was a little bit odd. So there were 3 objects or carts in a straight line. I think the book had the y-intercepts wrong because I think they're flip-flopped, but those aren't really relevant to what's going on here, by the way. So you had a 300-gram cart, a 200-gram cart, and a 400-gram cart, all initially at rest. You had things where like you pushed a plunger and it pushed them apart. So you need the idea is that the initial momentum is equal to the final momentum, which would equal 0, since everything was at rest beforehand. So the 200-gram cart went to the right in a positive direction at 0.53 meters per second, because that's the slope. 300-gram cart went in the negative direction, negative 0.41 meters per second, because that's the slope. And then we're trying to find out what the 400-gram cart would do. So looking at the momentum of these, and these are non-standard units because they're gram meters per second, but since we're just trying to find speed, it doesn't really matter because the mass is going to divide back out. So I get negative 17 gram meters per second plus 400 grams times x. Unfortunately, I used x as the velocity. I should have just said v, so sorry about that. So I ended up getting that x is equal to negative 0.0425 meters per second. So the 400-gram cart is going to go 0.0425 meters per second to the left based on this graph and conservation of momentum. Next couple, you've got 2 people on ice. They're going to hit each other in a perfectly inelastic collision. I had initially boogered up my numbers. So it's 210 kilogram meters per second to the left, 187.5 north. So when we do that, we get a final momentum of 281.5 kilogram meters per second and an angle. So the inverse tangent will give me the angle north of west. Make sure you're in degree mode. To get the velocity, we use the net momentum divided by the total mass, which is now both of the people run together, so that's 135 kilograms. And so that ends up being 2.08 meters per second at 41.8 degrees north of west. To find out how long it takes to get to the edge of the rink, said the rink had a 50-meter diameter, so that's a 25-meter radius. So you're starting at the center, and it doesn't matter what direction you're going to go. You need to go 25 meters to get to the edge of the rink. So I just did change in position over velocity would equal the time. That was around 12 seconds. 45. I like this problem. You're trying to rescue someone in the most ridiculous way possible. We have a rocket, 1 kilogram, package 5 kilograms. You need to find the minimum speed, or the speed that the rocket has hit. So first of all, you got to find the time for the package to fall to the ground. So vertical and horizontal motion are independent of each other. So I use y equals 1/2 gt squared, so that's 6.39 seconds to fall. Then, to get across the 30 meters, the rocket and package need to therefore go 30 meters in that time, so that's about 4.69 meters per second. The package is initially at rest, and you want to find the speed of the rocket. So I use conservation of momentum, because that works during all types of collisions, whether they are elastic or inelastic. And so I've got 1 kilogram times v plus 5 kilograms times 0 meters per second equals 6 kilograms times that final velocity that I needed. That says the rocket's going to be going basically 5 times faster, or 6 times faster, I guess. 4.69 times 6. So about 28 meters per second would be enough for the rocket to cause the package and rocket combined to go that speed. Problem 59 deals with subatomic particles hitting each other, and again, it's just a conservation of momentum. The units are different, so I've shown you a couple problems now where the specific units don't matter as long as you're just trying to find speed or mass. Momentum's conserved as long as the units are consistent throughout the problem. So I've got a 1 atomic mass unit moving at 2.5 million meters per second to the right. It rebounds back and loses a quarter of its speed, so I multiplied the rebound speed or velocity as negative because it's going the opposite way, and then times 0.75. And then the nucleus that was hit is traveling 3.12 times 10 to the 5th meters per second in the same direction that the proton was traveling initially. And we're trying to find the mass. So I simply get momentum initial plus momentum final. The only thing I don't know is the mass. So that says that the mass is 14 units. So that might be something like an isotope of carbon or somewhere like that, or oxygen or something like that. Nitrogen, maybe nitrogen. Okay. So this one's a vector problem. So it says it's a perfectly inelastic collision. You have these 3 things coming together. So big idea, let's solve things. And this is kind of like a unit vector problem. So we're looking at the x momentum and y momentum. Key thing here is that you need to look at that conservation of momentum, not just velocities, because the objects have different masses. So I'm converting all these things into momentum first. So I've got this object going down to the right, and so the momentum is m times v. So this would be mv cos theta. This is mv sine theta. I'm using negative is down, positive is up. Right is positive, left is negative. So for this, I get 113 gram meters per second to the right and 113 gram meters per second down. For 2, it's easier. It's only going to the left, so I have a negative momentum there, nothing going vertically. For 3, it's easier. I have nothing horizontally, only going vertically up. So I add all the momenta in the x direction and the momenta in the y direction, and I end up getting these numbers. Okay, so Now I'm going to use those and draw a vector diagram. So remember, the arrows are tip to tail. So 23 gram meters per second to the right, 73 gram meters per second down. I get a resultant momentum of 76.5 gram meters per second. Take that divided by the total mass, which is 20 plus 30 plus 40 grams, and I get the resultant speed. Get the resultant direction. I use inverse tangent of this. And so it's 73 degrees south of east, or you could have said 17 degrees east of south. So that's another way you could have said that. So I'll write that down there. Hopefully that helps, and hopefully those make some sense. Thanks.